Chapter 13: Saturated Fats and Structural Stability. Saturated fats function as structural inputs that influence how membranes maintain shape, resist deformation, and control permeability under continuous stress. Their defining feature is the absence of double bonds along the fatty acid chain, which allows them to pack tightly within the lipid bilayer. This packing reduces free movement between molecules, increasing membrane density and mechanical stability. When incorporated into membranes, saturated fatty acids contribute to a structure that resists disruption, preserves gradients, and maintains consistent behavior across varying conditions. Membrane stability depends on the balance between rigidity and flexibility. Saturated fats shift this balance toward controlled rigidity by limiting the degree to which lipid chains can bend and move. This reduces the formation of gaps within the bilayer, decreasing permeability to ions and small molecules. The result is a membrane that holds electrical gradients more effectively and supports the function of embedded proteins that rely on stable conditions. Without sufficient structural support, membranes become more susceptible to deformation and leakage, altering how signals and substrates move across them. Mechanical forces act continuously on cellular membranes, particularly in tissues exposed to pressure, flow, or repeated deformation. Saturated fats enhance the ability of membranes to withstand these forces by reinforcing the bilayer against distortion. This is especially relevant in systems where structural integrity directly influences function, such as vascular endothelium and neuronal membranes. A membrane enriched with saturated fatty acids distributes stress more evenly, reducing the likelihood of localized failure that can disrupt signaling or increase permeability. Cholesterol interacts with saturated fats to further regulate membrane structure. The presence of saturated chains provides a framework within which cholesterol can integrate effectively, modulating membrane properties without destabilizing the bilayer. This interaction supports the formation of domains that organize receptors and signaling complexes. When saturated fats are present in appropriate proportions, cholesterol contributes to maintaining consistent membrane behavior. Without this structural context, cholesterol cannot exert the same stabilizing influence. Saturated fats also influence how membranes respond to temperature and metabolic conditions. Their tight packing reduces the extent to which membranes become overly fluid at higher temperatures or under conditions that promote increased molecular movement. This maintains functional consistency across a range of environments, ensuring that membrane-dependent processes such as signaling and transport remain stable. Incorporation of saturated fats into membranes occurs gradually through remodeling cycles. As new lipids replace existing components, the proportion of saturated fatty acids influences the long-term structural characteristics of the membrane. This cumulative effect means that dietary input contributes to membrane stability over time rather than producing immediate changes. The system integrates these inputs into its architecture, adjusting properties based on the available substrates. Energy efficiency is indirectly supported by structural stability. Membranes that maintain tight control over permeability reduce the energy required to sustain ion gradients and support transport processes. This lowers the demand on mitochondrial function, allowing energy to be allocated more effectively across cellular activities. When membranes are less stable, increased leakage requires additional energy to restore conditions, reducing overall efficiency. Saturated fats therefore contribute to the structural integrity of membranes by enhancing packing density, reducing permeability, and supporting consistent behavior under stress. Their role is defined by how they integrate into the lipid bilayer and interact with other components to maintain a stable boundary. This stability underlies the proper function of systems that depend on controlled gradients, organized signaling, and mechanical resilience because the membrane provides the physical framework through which these processes are executed. Saturation and membrane rigidity. Membrane rigidity is determined by how tightly lipid molecules pack within the bilayer, and saturation directly controls this packing behavior. Saturated fatty acids have straight hydrocarbon chains that align closely with one another, minimizing space between adjacent molecules. This alignment reduces lateral movement within the membrane, increasing density and limiting deformation. As the proportion of saturated lipids rises, the bilayer becomes more ordered, and its physical resistance to bending, stretching, and compression increases. This increased order reduces permeability. Tightly packed lipids create fewer transient gaps through which ions or small molecules can pass. Ion gradients depend on this containment. When membranes hold their structure, electrical potential can be maintained with minimal leakage, supporting processes such as signal transmission and active transport. As saturation decreases and packing loosens, permeability increases, and gradients dissipate more quickly, requiring greater energy input to restore them. Rigidity also affects how proteins embedded within the membrane behave. Ion channels, receptors, and transporters operate within the constraints of the surrounding lipid environment. A more rigid membrane stabilizes the conformation of these proteins, allowing them to transition between states in a controlled manner. This supports consistent signaling and transport. When the membrane is less ordered, protein behavior becomes more variable as the surrounding environment no longer constrains their movement with the same precision. Mechanical stability emerges from this rigidity. Membranes are subjected to continuous forces, including shear stress, pressure, and cellular movement. Saturated lipids provide resistance to these forces by maintaining structural integrity under deformation. This reduces the likelihood of localized failure, where small disruptions in the bilayer can propagate into larger defects that alter function. A rigid membrane distributes stress more evenly, preserving its properties across different regions. Cholesterol integrates into this environment and modulates rigidity further. In a membrane with sufficient saturated lipids, cholesterol fits between aligned chains, reinforcing packing and reducing fluidity without eliminating flexibility. This creates a state where the membrane remains stable but not brittle. If saturation is too low, cholesterol cannot stabilize the structure effectively, and if saturation is too high without modulation, the membrane can become excessively rigid, limiting necessary dynamic behavior. Rigidity must therefore exist within a functional range. Membranes require enough order to maintain gradients and support protein function, but also enough flexibility to allow processes such as vesicle fusion, signaling, and transport. Saturated lipids establish the structural baseline, while other components adjust this baseline to meet functional demands. The balance between these elements determines how the membrane behaves under different conditions. Over time, the level of saturation within membranes is shaped by the fatty acids available for incorporation. Remodeling cycles gradually shift composition, adjusting rigidity in response to input and demand. This process does not produce immediate changes, but alters membrane properties through cumulative replacement of components. Saturation and membrane rigidity therefore define the physical state of the bilayer, influencing permeability, protein behavior, and mechanical resilience. By controlling how tightly lipids pack, saturation sets the conditions under which cellular processes occur. When this structure is maintained within an appropriate range, membranes provide a stable yet responsive environment that supports consistent function across varying conditions. Resistance to oxidative damage. Resistance to oxidative damage is determined by how vulnerable membrane lipids are to chemical attack and how effectively the system contains and repairs that damage when it occurs. Oxidation targets the double bonds within fatty acid chains. These sites are chemically reactive and can be altered by reactive species, initiating a chain reaction that propagates through adjacent lipids. Membranes with a higher proportion of unsaturated fatty acids present more of these reactive sites, increasing susceptibility. In contrast, saturated fatty acids lack double bonds and therefore provide fewer entry points for this process, reducing the likelihood that oxidative reactions will begin within the bilayer. When oxidation is initiated, it alters the structure of affected lipids. The products of this reaction no longer fit within the membrane in the same way as intact fatty acids. This disrupts packing, increases permeability, and interferes with the behavior of embedded proteins. The initial event is localized, but if not contained, it spreads as adjacent lipids are affected. This propagation changes the physical properties of the membrane, leading to increased ion leakage and altered signaling. Resistance to oxidative damage, therefore, depends on both preventing initiation and limiting propagation. Membrane composition influences both of these factors. A bilayer with tighter packing and fewer reactive sites reduces the probability that oxidative reactions will begin. Once initiated, dense packing also limits the spread of the reaction by restricting the movement of reactive intermediates. This containment reduces the scale of structural disruption and allows repair processes to address the affected area without widespread damage. Antioxidant systems operate within this structural context. Lipid-soluble molecules positioned within the membrane can neutralize reactive species and interrupt propagation. Their effectiveness depends on distribution and accessibility, which are determined by membrane organization. When the bilayer maintains structure, these protective components remain properly positioned to intercept reactions as they occur. Disordered membranes reduce this effectiveness by altering distribution and allowing reactive species to move more freely. Repair mechanisms follow containment. Damaged lipids are removed through enzymatic processes and replaced through remodeling cycles. This requires recognition of altered components and sufficient energy to support turnover. Efficient mitochondrial function supports these processes by providing the ADP necessary for enzymatic activity and synthesis. When energy supply is limited, damaged lipids persist longer within the membrane, extending the period during which structural properties are compromised. The consequences of oxidative damage extend beyond the membrane itself. Increased permeability affects ion gradients, altering electrical and signaling conditions within the cell. Products of lipid oxidation can also act as signaling molecules, influencing inflammatory pathways and cellular responses. The extent of these effects depends on how well the initial damage is contained and repaired. Resistance to oxidative damage, therefore, reflects a combination of structural composition and dynamic maintenance. Membranes that limit reactive sites, maintain tight packing, and support effective antioxidant and repair systems are less susceptible to disruption. When these conditions are met, oxidative events remain localized and are resolved without significant impact on function. When they are not, damage spreads and persists, altering membrane behavior and affecting the processes that depend on its integrity because the structural framework has been chemically modified and not adequately restored. Thermal and electrical stability. Thermal and electrical stability emerge from how tightly the membrane controls movement at both the molecular and ionic level. Temperature increases kinetic energy within the bilayer, causing lipid chains to move more freely and increasing the probability of transient gaps forming between molecules. If the membrane lacks sufficient structural constraint, this increased motion leads to elevated permeability, loss of ion gradients, and disruption of protein function. Saturated fatty acids counter this effect by maintaining alignment and limiting chain movement even as temperature rises. Their straight structure reduces the degree of disorder that can develop under thermal stress, preserving the integrity of the bilayer across a wider range of conditions. This thermal resistance directly influences electrical behavior. Membranes function as dielectric barriers that separate charge across a defined distance. The stability of this separation determines whether electrical gradients can be established and maintained. When thermal motion increases permeability, ions move more freely across the membrane, dissipating voltage differences and reducing the efficiency of processes that depend on controlled charge separation. A membrane with sufficient structural order resists this leakage, maintaining capacitance and allowing electrical signals to propagate with precision. Electrical stability also depends on the uniformity of the membrane. Variations in lipid composition create regions with different conductive properties, which can distort signal transmission and alter how charge is distributed. Saturated lipids contribute to uniform packing, reducing heterogeneity in the bilayer and supporting consistent electrical behavior across its surface. This uniformity is critical in systems that rely on rapid and coordinated electrical changes, such as neuronal signaling and muscle contraction, where small disruptions in membrane properties can alter timing and amplitude of signals. Cholesterol modulates both thermal and electrical stability by integrating between lipid molecules and adjusting how they respond to temperature changes. In the presence of saturated fatty acids, cholesterol restricts excessive movement at higher temperatures while preventing the membrane from becoming too rigid at lower temperatures. This creates a controlled range of fluidity that maintains both mechanical and electrical function. Without this interaction, membranes either become too permeable under heat or too rigid under cooling, each state impairing function in different ways. Protein behavior is also tied to these properties. Ion channels and transporters depend on stable electrical gradients and consistent membrane thickness to operate correctly. Thermal instability alters the surrounding lipid environment, changing how these proteins shift between states. Electrical instability reduces the gradients that drive their activity. When both forms of stability are maintained, protein function remains predictable, allowing coordinated signaling and transport across the membrane. Energy systems depend on this stability as well. Mitochondrial membranes rely on tightly controlled proton gradients to drive ADP production. Increased thermal motion or structural disorder allows protons to leak across the membrane, reducing the efficiency of energy conversion. Structural integrity limits this leakage, preserving the gradient and maintaining output. This links membrane composition directly to energy efficiency at the cellular level. Thermal and electrical stability therefore arise from the same underlying structural conditions. A membrane that maintains tight packing, controlled fluidity, and uniform composition resists temperature-driven disorder and preserves charge separation. These properties allow gradients to persist, signals to propagate accurately, and energy systems to operate efficiently because the boundary itself continues to enforce the separation and containment required for these processes to occur. Structural necessity under stress. Stress exposes the membrane as a load-bearing structure rather than a passive boundary. Mechanical force, oxidative pressure, thermal fluctuation, and signaling intensity all converge on the bilayer at the same time. Each of these inputs increases movement within the membrane, distorts lipid packing, and challenges the ability of the system to maintain separation between internal and external environments. The requirement is not flexibility alone. The requirement is controlled resistance that preserves containment while allowing necessary function to continue. Saturated fatty acids contribute to this condition by maintaining alignment under force, limiting deformation, and preventing the formation of discontinuities that would allow uncontrolled exchange. Mechanical stress acts first at the level of shape. Shear forces from blood flow, compression within tissues, and deformation during movement all push against the membrane. If lipid packing is loose, these forces create localized thinning and expansion, increasing the likelihood of transient defects. These defects allow ions and small molecules to cross in unregulated manner, altering gradients and initiating downstream signaling that does not reflect controlled input. When saturated lipids are present in sufficient proportion, the bilayer distributes force across a larger area, reducing localized strain and maintaining thickness. The structure holds its geometry instead of collapsing into points of weakness. Chemical stress follows through oxidation and reactive intermediates. Under these conditions, membranes with higher structural order limit both the initiation and spread of damage. Fewer reactive sites reduce the probability that oxidation begins, and tighter packing restricts the movement of reactive species once it does. This containment prevents the cascade from expanding across the bilayer. Without this constraint, damage propagates, altering multiple regions of the membrane at once and compromising function beyond the initial site of stress. Thermal stress increases kinetic activity and amplifies both mechanical and chemical challenges. As temperature rises, lipid movement accelerates, and the likelihood of gap formation increases. A membrane that already lacks structural density cannot compensate for this increase in motion, leading to rapid loss of containment. Saturated lipids reduce the magnitude of this change by limiting how much additional movement occurs under heat. The membrane shifts, but within a constrained range that preserves function. Signaling stress introduces a different form of load. High signaling demand requires repeated conformational changes in receptors, rapid cycling of ion channels, and continuous vesicle fusion and fission. These processes exert localized strain on the membrane and require a stable environment to operate correctly. Structural integrity ensures that these repeated events do not degrade the surrounding bilayer. When structure is insufficient, signaling becomes noisy. Receptors cluster irregularly, channels open and close unpredictably, and the system begins to interpret internal instability as external input. Energy demand increases under all forms of stress. The cell must maintain gradients, repair damage, and support signaling at a higher rate. Structural stability reduces the energy required to perform these tasks. A membrane that holds its integrity minimizes leakage and limits the extent of repair needed, allowing energy to be directed toward function rather than compensation. When structure fails, energy is diverted toward restoring conditions that should have been maintained by the membrane itself. Stress therefore reveals whether the membrane can enforce boundaries under load. Saturated fats contribute to this enforcement by stabilizing packing, reducing deformation, and limiting the spread of damage. This is not an enhancement layered onto function. It is a requirement for function to persist when conditions deviate from baseline. When structural integrity is maintained, the system continues to operate within defined parameters. When it is not, the boundary becomes inconsistent, and every process that depends on controlled separation begins to degrade because the physical framework that supports those processes is no longer stable under the forces acting upon it.